The final session of the conference, and it's a great pleasure to introduce Steve Kerckhoff from Stanford, who's going to be talking about deformations of hyperbolic three-manifolds and other geometries.
Hi. So I want to thank the organizers, and particularly Harold and Misha, for the invitation to come here. It's my first trip to Brazil and having a great time. I must confess I've yet to see my first monkey, and time is running out, but at any rate, I'm still optimistic. So I'm particularly pleased to have been invited here because I never done any work in minimal surfaces. I have worked many different parts of geometric structures on three manifolds and so on, and I've actually changed my title slightly because I tried to tweak it a bit so that actually I think towards the end of the talk I actually will be able to say the words minimal surfaces with a straight face. It will actually come up. This is going to be a sort of multimedia talk. I'm going to start on the blackboard as I wanted to do some preliminary background things that connects with things that have been talked about a certain amount already in the conference, and then we'll move to the slides. But the main theme I want to have throughout the talk is that although we think of hyperbolic three manifolds, particularly closed ones or finite volume complete structures, as sort of unique objects, they're rigid by Mostow rigidity and so on, that you actually, by allowing incomplete structures or structures with singularities, will be more the way I'll be talking about them here, you actually can see whole deformation theory and begin to see sort of two things I'll emphasize. The first one is how to see, and this was already brought up in Joel Haas's talk, how hyperbolic structures on different three manifolds are actually closely related. So you see a sort of family of hyperbolic structures on different manifolds that are still geometrically closely related. And then the main topic of today's talk will be to also show how this sort of deformation theory leads you to think about, even if you're just interested in hyperbolic geometry to start with, to geometric structures of another sort, some of the other Thurston geometries, and in fact we'll even see some other more exotic geometries coming up. So again, the emphasis here is sort of on the whole family of three manifolds and families of structures. So the first theorem I want to talk about has been mentioned a number of times, is Thurston's hyperbolic Dane surgery theorem. So we're going to take M3 to be hyperbolic three manifold, but I want it to be finite volume and I want it to be non-compact. Let's assume it, say, just has one cusp, and it'll be orientable. So we've seen the picture of sort of rough scheme of what this looks like. Has this one cusp, you have some sort of topology in here, and then the end of the manifold is foliated by these tori whose intrinsic curvature is 0. They go down by just scaling sort of exponentially as you go down here. I guess these are CMC surfaces as well to connect with our discussion so far. But from this single non-compact three manifold, topologically we can get an infinite number of compact manifolds by doing Dane filling. And so we truncate in this fashion here. We take a solid torus, so this is just a disk cross S1. And then we glue the boundary, this boundary torus, to the boundary torus here. But we do so, there are a lot of different ways of doing this. In particular, this curve here that bounds a disk, so-called meridian, we can glue it, this gluing operations essentially determined by the isotopy class of a simple closed curve, which can be very complicated, much more so than I've drawn here, on the boundary of the three manifold. And we glue this in along there so that this curve goes to this curve. So let's call the curve that the boundary of the meridian goes to gamma. And we'll talk about the resulting closed manifold. We'll call that M gamma. Okay, and they're parameterized by this isotopy class of curves here. And in particular, such gammas are in sort of one-to-one correspondence if you choose a basis, AB, which is just a z plus z, where these are relatively prime. So there's effectively a doubly infinite number of ways of doing this. I should say that the pi 1 under this condition here of the torus injects into pi 1 of the three manifold. It's an incompressible surface. But then after we attach the solid torus here in this way, so in pi 1 of M gamma, gamma goes to the trivial element. Okay, so we've killed off this curve and ended up with a closed three manifold. And then Thurston's hyperbolic Dane filling, this process is called Dane filling, says that for all but a finite number of gammas, the resulting manifold has a hyperbolic structure. So from this, and in this way, we of course get an infinite number of related hyperbolic, closed hyperbolic manifolds. So again, by allowing, and we'll talk a little bit about where this comes from, a deformation of the structure, the complete structure, where actually on a single manifold, we end up with an infinite number of hyperbolic, closed hyperbolic three manifolds. In particular, this finite number can be 0. In the case of, like that Mark talked about, when it's a knot complement, if you just stick the solid torus in such a way that you get S3, then of course you can't get a hyperbolic structure. But in many cases, as he mentioned, that's the only way you get something non-hyperbolic. So the ones that are not hyperbolic are called exceptional surgeries, and that's one of the things he was discussing in the previous talk. So I guess the other thing, and this was important in Joel's talk, Joel Haas's talk, that if we let these, say, take any basis here, if we let these coefficients of the curve that we're killing off here go off to infinity, then in fact the geometry, so this geometry of M gamma approaches the geometry of the cusp manifold. You get a very short geodesic that corresponds to the core inside here. That's very far off from the bulk of the manifold there. And the rest of the manifold gets closer and closer to the geometry of your original cusp manifold. Now, the reason you have this kind of structure is what Thurston actually does is he perturbs the complete structure to incomplete structures, so nearby through incomplete structures. And he does it in such a way that you have some control over what the completion looks like. And you do it in such a way is so that the completion gives a smooth hyperbolic structure on M gamma. So this is why, because it's just a perturbation theory, you know that the approximate structures look very, very much like the geometry of the complete structure. Now, even though this is sort of an amazing theorem, the proof is actually extremely easy. The main idea is you do a dimension count to see there are perturbations in the sense that the holonomy changes. You use Mostow rigidity to say the nearby structures, or Mostow-Prasad structures theorem to say that the nearby structures are not complete. So you have incomplete structures. You study how the holonomy of the structures changes. And so this is, as I say, this is basically just an open mapping. So it uses Mostow rigidity and some sort of open mapping statement. So the finiteness is a very non-effective result. So as a result of this, this is a sort of non-effective in the sense of there are no estimates. Now, since the time of this, there have been various ways of making this process more effective and more getting estimates and so on. Mark actually mentioned this before, so using Gromov and Thurston 2-pi theorem. And actually, Mark, so this is the 2-pi theorem. And separately, Ian Agel. So this theorem said that if you look on the sort of maximal boundary of the maximal cusp, if the curve has length greater than 2 pi, you can put a negatively curved metric on it, and there, once that tells you it has the topological properties that hyperbolic manifold should have, if and only if by Perelman, and then use Perelman to conclude it's actually hyperbolic. So they improved this to a 6 theorem, which in certain parts of the US, this is an improvement anyway. But it doesn't give you really any information about how different the structures are. So there's a different point of view that did with Craig Hodgson, which is more analytic and also gives you both not only effective bounds on, so I should say that from this you get uniform, from this statement here and then from our work, you get a uniform upper bound on this finite number over all hyperbolic 3 manifolds. Okay. So whereas this just says for any given one, there's some upper bound, some finite number. So this analytic process involves sort of a Hodge theory for the deformation of the tangent space, so the character variety and so on. But the part of the point is that because it uses estimates, you actually get not only estimates on the number of exceptional surgeries, but also on the change in the geometry. So in particular, one of our approaches was to vary through some singular structures called cone manifolds. So these are going to be hyperbolic structures, say on M gamma here, but where when you attach the solid torus, inside the solid torus, there's going to be a geodesic, but it will necessarily have it will generally have singularities transverse to the core there. So there'll be some geodesic in the center. We have gamma on the boundary. Over here. But this is not a smooth disk cutting across here. In fact, it looks like, well, you might guess as a result of the name, there's this side is identified to this side, and there's an angle alpha here. This is sitting in the hyperbolic plane. And so you see all these sort of two-dimensional cones going around here, and it's the same alpha going all around there. So it's not too hard to, in fact, it follows from Thurston's original work that for any gamma, can find so in this alpha here is called the a cone structure. It's called a cone manifold structure, and alpha is called the cone angle, at least with small cone angle. So you think of the cusp manifold when this is the thing I erased here, where this sort of the core is all the way out at infinity as being cone angle 0. You can, for any gamma, you can perturb the structure in such a way that you can at least get a hyperbolic structure on M gamma, but allowing some kind of singularity like this. And then the idea is to attempt to increase the cone angle up till 2 pi. And of course, Thurston's theorem says for all, well, a version of Thurston's theorem says for all but a finite number of gammas, you can do that. You can be successful. Okay. So part of what we proved, in fact, is that such cone manifolds like this are rigid rel cone angle. This is at least when alpha is at most 2 pi. So you can think of this as a sort of variant of Mostow-Prasad rigidity that says the complete structures are rigid as long as you keep it complete. So here we keep, instead, we keep the angle the same. It says there's no way to actually vary the hyperbolic structure. Okay. Now the rigidity like this turns into a statement about if you change the cone angle a certain amount, then it only changes the geometry a certain amount. And that's where the effective estimates come from. I should say, I think my original title was Deformations, Hyperbolic 3 Manifolds, and Boundary Value Problems. So you can view this as finding a hyperbolic structure on the manifold where you take out a tubular neighborhood of the core and want a certain boundary value structure on here. But that's not really the main theme of what I'm going to do after this. So this is sort of a success story in the sense that we mostly get hyperbolic structures, but what happens when this fails? For example, if we took a knot complement that's hyperbolic and we just do trivial Dane filling, so you get S3 back, we obviously can't get all the way to 2 pi because that would give me a hyperbolic structure on the 3 spheres. So if this family degenerates, and so the theme of the rest of the talk is going to be that at least in some situations, this leads to other, in some cases, it leads to other geometric structures. Okay, so now we go to the second medium. So before talking about the three-dimensional context here, I want to do a couple of two-dimensional examples that hopefully maybe will be fairly familiar. So this process of going from hyperbolic geometry to other geometries called transitional geometry, and here's a couple two-dimensional versions of that. We start with a pair of identical hyperbolic triangles. Let's assume, in fact, they're equilateral triangles. So that's just equivalent to saying the three angles there are the same. And we know for small angles, including 0, we can find such a hyperbolic triangle. Take two of those, glue them together. Okay. So what do we see? Well, we get a smooth structure on the inside and on the edges, but at the points that were the vertices, again, assuming the angle is non-zero, you actually get a cone structure, in fact, exactly the kind of cone structure we saw over there. So we have, in this case, 3 cone points. So we have a 2-dimensional cone manifold with 3 cone points. We let alpha go to 2 pi over 3. This means this by Gauss-Bonnet theorem is the area of this thing, so the area goes to 0. But we can rescale it just by, and since the area is going to 0, if we say rescale it so the area is equal to 1 at each stage, then the limit will have curvature 0, and so we'll actually see a Euclidean cone manifold in the limit. And so what you see is, in fact, just the double of the pi over 3, pi over 3, pi over 3 equilateral Euclidean triangle. Now you can do the same thing from the other side with spherical triangles, where you start above 2 pi over 3 for the cone angles, or pi over 3 for the angles of the triangles. Again, you get a formula for the area as alpha goes to 2 pi over 3 from above. It again degenerates down to a point. By rescaling, you get a Euclidean structure. So this is a kind of picture I want to be looking at. Start with a family of hyperbolic structures. It degenerates in some way. By doing some sort of rescaling or something, we end up, in this case, with Euclidean. In other cases, we'll end up with other structures. And then you can actually push through. Everything in sight is a 2-dimensional structure, but the geometries change, and you can sort of go all the way through to spherical structures. So here's another example. So we take a hyperbolic torus with a single cone point. Again, you could have that angle be 0, and we'd have a complete structure. Sorry. The area is equal to 2 pi minus alpha, and as alpha goes to 2 pi, the area goes to 0. Now you can do this in such a way that, again, everything just collapses down to a point. You can rescale, blah, blah, blah. But what I want to do instead is do it in such a way that it collapses in a non-uniform way, and say, for example, the gluing of 1 to 1 there, suppose that length stays the same and is just gluing 2 to 2 there, so it sort of collapses down to a single arc of whatever that length was. Now in this case, if you did a uniform rescaling, you get something non-compact, so we do something along the lines of a kind of vertical rescaling. Now, you would think, okay, I'm just going to get a flat something or other, but in fact, if you look near this cone point here, if you think about what's happening, so in all the approximates, we're getting close to 2 pi, we're attaching that side to that side, but then we're also rescaling only in one direction. So the limit of that is not going to be a trivial rotation, it's actually going to be a shear. So we'll see a geometry, in fact, in 3 dimensions that actually gives you this kind of information, this extra information that will come up. Okay, so we'll talk about that a little more precisely, what I mean by rescaling vertically, in a minute. Okay, so again, we're so far just talking about hyperbolic structures, say on 3 manifolds. So, for example, if you take the figure 8 knot, it has a hyperbolic structure on its complement, a complete hyperbolic structure. But we can imagine doing just the trivial filling to get S3 back. And it's not hard to show that, in fact, you can find hyperbolic structures with cone structures. So again, there's a geodesic along the core of the filled-in knot there. But you take a cross-section, then you have some singularity. Again, you can check that the volume goes to 0. And in fact, this is like the first example, the triangle example. Everything kind of collapses uniformly. So again, you can do the same thing of rescaling uniformly. Again, you realize you get a Euclidean cone manifold. It'll have cone angle 2 pi over 3. It's actually an orbifold. So again, we see a family of hyperbolic structures degenerating essentially to a point. Rescaling, we get some kind of Euclidean structure. Now you can actually come at this Euclidean structure from the other side with cone angles You can go up to 2 pi over 3, up to pi, and then again back down to 2 pi over 3. So actually this pi angle here, for those of you, this is a two-bridge knot, so it has a two-fold cover, which is a lens space, so it in fact has a spherical structure. So that's it. You know, you can at least, there's a spherical structure in this case, and you can actually decrease the cone angle till you get here, but again, the area, the volume collapses. So that's sort of, again, this is a kind of well-known phenomenon that people have thought about for quite a while, but I want to sort of talk about some more subtle kinds of degenerations that are more like the second two-dimensional example that I mentioned. So I want to set up a little bit more of an algebraic setting where I don't just talk about metrics and rescaling. And in particular, this will fit better with the next example I do, but just to see how it works in this case. So this is sort of algebraic. I'll do it in the three-dimensional context, but this works in any situation. So we have pi1 of M3, my original manifold, the complete manifold, or if you like, just take the manifold with a singular structure, remove the singular locus. We now have a non-compact, incomplete manifold. So we have, we call that group pi. So we have a family of representations from pi to the isometry group of hyperbolic 3 space, which I'm going to write maybe somewhat less familiarly as SO31. The representations collapse. When this thing collapses, we end up with a representation from pi to the stabilizer of a point, which is just SO3. And then, so this is for, say, S bigger than 0. And then coming from the other side, we have the isometries. Spherical isometries, we have this. So we get a family here and here. This collapses really to a completely, there's no geometric structure there. But if you remember what the isometries of Euclidean space look like, there's a translational part. And then this goes down to SO3, and in fact, this is a twisted product. And so what we have is a representation. Is this annoying, as annoying to you as it is to me? Yes? All right. All right, well. So this is a limiting object, and what we actually want is to lift this to a representation into here. Okay. And the way we actually are doing this, the algebraic version of this, is we actually conjugate these things in SO3 within projective geometry, within PGL4, in such a way that we actually get convergence of the conjugated things to this lifted object here. Okay, so that's the algebraic version of this rescaling idea, where we have these things here. We do a conjugation in the sort of bigger Lie group, in this case the projective group PGL4, and do it in such a way that this no longer degenerates but stays three-dimensional all the way through S equals 0. Okay, so here's another example of a kind of transitional thing. Again, this has been brought up, for example, in Zeno's talk. We start with a Fuchsian group, just a hyperbolic structure, say, on a closed genus G surface. But think of it as sitting in hyperbolic three-dimensional geometry. When you divide out by that group, you get a three-dimensional manifold that is surface cross R, and it has a totally geodesic surface inside. And then outside, this has an infinite amount of volume going all the way out to the boundary. It has a kind of conformal boundary out there. Now, we can deform this not just within the Fuchsian world, but within the quasi-Fuchsian world, in other words, within PSL2C, or if you like, SO31, to get a so-called quasi-Fuchsian group. The resulting three-manifold is still a surface cross R with conformal boundary. It no longer has a totally geodesic subsurface inside of it, but it's got some wiggly surface in there. And if it's close to being Fuchsian, in fact, we've heard that there's, in fact, going to be a unique minimal surface inside there. But in any case, one way to turn this into a compact object and finite volume is to take the convex hull of this limit set up here in the hyperbolic sense. That ends up being a surface that has boundary, which is totally geodesic, but it's bent along a so-called geodesic lamination. And these will be for a lot of values near the Fuchsian and a lot more. Actually, this will actually have finite volume. So if you're not familiar with the concept of lamination, you can just imagine that this is a hyperbolic, in this case, genus 2 surface, but it's totally geodesic, except it's bent along some geodesics. Okay, and so this is actually a convex thing. It's bent on the top, going down. On the bottom, it's bent going up. So there's a still open question about the question of which laminations, mu and nu, can be realized in this way, and whether these two laminations actually completely determine which quasi-Fuchsian group you have. Okay. There's a fair amount of, so these mu and nu are called the bending lamination. They're a lamination with a transverse measure, which tells you how much has been bent. Again, you can just think, in fact, we'll quickly go to that case, where the top lamination and the bottom lamination are two simple closed curves, or collections of simple closed curves. And the weight of them is the amount that they've been bent. But the general statement is the necessary condition for mu and nu to be bending, the union bending laminations, is the pair of them fill up the surface. And that just means if you realize the two laminations on a single surface, the complementary region is just a bunch of compact polygons. And again, that means if there are simple closed curves, then every other simple closed curve intersects one, or I mean, every simple closed curve intersects one or the other. So it really completely fills up surface. You can sort of see that that has to be the case, because if there was a part of the surface that wasn't sort of covered, there's a totally geodesic subsurface, the three-manifold would actually collapse down in a certain place. So, and then there's a condition that, so curly S here is just the laminations that correspond to collections of simple closed curves. And so in the case that you have simple closed curves, you can't bend more than pi. That's, again, sort of obvious, otherwise you'd run into yourself. So these are necessary conditions. And then a theorem of Bonahon and et al. Is, in fact, every such pair of laminations in this set of filling laminations, in fact, can be realized. There is a quasi-Fuchsian group that has that as its boundary of its convex core. What's not known is a uniqueness statement that mu and nu actually determine completely the quasi-Fuchsian group. This is known to be true in the case when the top and the bottom laminations are simple closed curves. And this actually, as we'll see in a second, you can imagine, in particular, if the top and the bottom are bent along simple closed curves, and we double, we'll have a hyperbolic manifold, and in fact, it's just a surface cross S1, but it'll be smooth everywhere except where we bent. And there, where we bent, we'll have a cone manifold structure just like before. So this is very similar to the doubling we did in the surfaces. And because of the local rigidity statement I mentioned down here with Craig Hodgson, you get a local rigidity in this case, and then they have some global results that allows you to push this to a global statement. But we don't have a kind of local rigidity statement in the more general situation. It is known, however, independently by work of Bonahon and series, that in fact there is a unique quasi-Fuchsian group with a given mu and nu when it's almost Fuchsian. So again, you see some version of what we saw for minimal surfaces being unique in the case of when it's almost Fuchsian. That's a little misleading because we certainly expect that it's unique even when you're far away from being almost Fuchsian, even though there'll be more than one minimal surface. Now you can ask, okay, we take, say, one collection of simple closed curves, another collection of simple closed curves with some weights, and then we let the amount of bending go to 0. So in that case, it's going to collapse to a Fuchsian group, right? One that has a totally geodesic thing in the center here. And in fact, you can ask what Fuchsian group, and you can in fact identify which Fuchsian group. It turns out that if you look at the length function, so the length, say, of those simple closed curves as a function on the Teichmuller space to R, when they fill up, well, each of these functions has some convexity properties in Teichmuller space. And when they fill up, in fact, you can prove there's a unique minimum to such a function. And because of the convexity results and so on, you're actually, that's what kind of leads into this uniqueness in the Fuchsian case. Okay, so I'm going to do what I said I was going to do. I'm going to now double so again, going back, we're going to take the case when the top and the bottom are bent along simple closed curves, and we can double the manifold. This gives me a topologically just the surface cross S1, but then we have singular curves corresponding to where the thing was bent on the top and the bottom. And this little wiggly guy here is that wiggly curve I had in the middle of the quasi-Fuchsian group. So again, we get the surface cross S1 with cone singularities corresponding to the closed curves that had the bending. As you let the bending go to 0 as the original quasi-Fuchsian group goes towards Fuchsian, then the angles alpha and beta go to angle 2 pi. Now, something has to happen because we can't just keep going and have a hyperbolic structure when those angles are 2 pi, because we'd have a hyperbolic structure on the surface cross S1, which obviously can't happen. And you can see what happens from the quasi-Fuchsian case. In fact, the whole 3-manifold just collapses, but it doesn't collapse to a point. It collapses to a hyperbolic plane, or the quotient of a hyperbolic plane. So it actually collapses essentially to a Fuchsian group. So we can ask, we saw before, okay, things collapse. We don't like collapsed structures. Is there some way to rescale or conjugate, as I described over here, in such a way that it transitions to something else? So before we had hyperbolic collapse to a point. The rescaling or conjugation gave me Euclidean. I kept going and got spherical. So what should I get in this context? Well, turns out that the thing that plays the role of Euclidean space is actually a new geometry. Well, it's not ever been studied before in a geometric sense that Jeff Danziger explored and did a lot of work in his thesis several years ago. And it goes under the name of half-pipe geometry, and I will actually explain that in a picture in a second. But at any rate, so I'll tell you some more about this geometry because it is a sort of new phenomenon. But then you can ask what comes out the other side. What's the analog of S3 of the spherical geometry? And it turns out the answer is anti-de Sitter geometry. So a Lorentzian metric, we no longer are in the situation of a Thurston-Riemannian geometry, but the natural structure, geometric structure that comes out is actually this ADS, and I'll write down some equations in the next slide to remind you what the structure is, the ADS geometry. Now this is actually of interest because actually these independently Jeff Mess a number of years ago in the 80s, and kind of had a lag. People didn't study it very much after him for a while, but there's been renewed interest. There's actually a whole sort of quasi-Fuchsian. So there are Fuchsian versions. Whoops. giving it all away. Fuchsian versions of these, and then again, there's a whole sort of theory of quasi-Fuchsian anti-de Sitter structures, so-called globally hyperbolic structures. And there's a lot of kind of analogies between quasi-Fuchsian geometry in the hyperbolic case and in the ADS case, but there was never any real understanding of why they were so closely connected. So in a sense, this gives a geometric reason. There's actually a geometric transition from the quasi-Fuchsian world through Fuchsian, through this sort of glorified, expanded Fuchsian and this half-pipe geometry that actually then leads to some of the structures that Jeff Mess was struck. So that's part of the reason I wanted to kind of push this. Is actually, as I say, there were sort of analogs in both theories, but this actually gives you a sort of a reason for it. So let me say something about, again, analogous to this picture over here. We have a one-parameter family of structures. So in this case, it's on this surface across S1 minus these two curves. That's the group we're interested in. The group you get by removing the singular locus of the cone manifold. To have a one-parameter family of hyperbolic structures, say up to a point, say where the parameter is 0, it collapses to something that preserves a hyperbolic plane. So this is just the isometries of hyperbolic plane. Coming out the other side, we have Lorentzian structures. So that group is, well, up to some sort of index 2 is essentially SO22. So if you remember, the sort of idea here is a hyperbolic geometry. In this form, we can think of looking at a quadratic form in R4 where S is equal to 1. It preserves the hyperbolic group, SO31, preserves this where S is equal to 1. In the case of the Lorentzian geometry, it's the case when S is equal to minus 1. Okay. And then in all of these cases, there's an H2 where it corresponds to where the coordinate, the last coordinate is equal to 0. So the idea is to take this one-parameter family of representations of the group into hyperbolic space, but think of it as sitting inside of PGL4, and then conjugate these things to a subgroup still of PGL4, and it'll be isomorphic to SO31, but that preserves this quadratic form where S is varying and in the limit goes to 0. Okay. So, and then similarly coming out the other sides where S was equal to minus 1, you can go from minus 1 towards 0, and again, look at the sequence of quadratic forms and that sort. So you actually see a bunch of groups preserving some kind of higher dimensional conic inside of 4 space. And by doing this conjugation process, you have things that are conjugate to hyperbolic here, conjugate to anti-de Sitter here. But by doing this conjugation, you pass through getting a 3-dimensional structure, where this 3-dimensional structure is this so-called half-pipe geometry. So this is, again, this is the SO, wherever it is, the SO21. That's what this, how this is embedded inside of PGL4. We actually, by conjugating, we get things to converge to something that looks like SO21 here, but then has a vector over here. Okay. Now, in the case of the, whoops, really giving everything away. Okay. All right. In the case of the Euclidean transition here, again, this was like SO3, and in fact, this the Euclidean group would actually have the vector going vertically here. And some of you may recognize this. This looks very similar to the isometry group of Minkowski geometry, flat Lorentzian geometry. And in fact, one way to interpret what this half-pipe geometry is it's sort of an adjoint or dual geometry to that. And the space can be thought of as a set of space-like planes sitting in Minkowski space. Okay. So that's an algebraic way of thinking of it. I have a picture here that can think of in terms of trying to understand what's happening geometrically. I couldn't draw this in R4, but if you go down a dimension, you imagine the light cone picture of hyperbolic 2 space and go down a dimension, but I'm now thinking of the hyperbolic 3 space. You have a totally geodesic. In this case, I've drawn an H1, but in the case we're interested in, that's actually a copy of H2. So in S equals 1, we preserve this conic as we, remember, as we now let S go from +1 towards 0, what is the invariant conic going to look like? Well, it starts getting stretched out in one direction, and the cross sections, instead of being circles, are ellipses. Okay. And then in the limit, so let's say like when S is a half, when in the limit, when S equals 0, the sort of conic actually just, this ellipse turns into 2 straight lines. And so, well, this is where the half pipe comes from, is in this dimension. The space looks like a half pipe. At any rate, it's the best we could do. So what are the set of isometries? I mean, they certainly preserve this degenerate quadratic form here, but they have more structure. It preserves the sort of straight lines moving along here. And in fact, there's a way to define a distance along those straight lines so that there's this copy of H2 here, but there are these sort of equidistant surfaces as you move along here. And that length, it takes lines to lines, but there's no notion of angle between those lines and let's say the hyperbolic space. That's sort of, you've lost any kind of geometry in that sense. So it's degenerate in that sense. And so in particular, if you look, say, at the stabilizer of a point, say there, it has to take lines to lines. It fixes that point. What do you see? Well, you see a shear. And in fact, this is exactly the geometry in 2 dimensions that I came up with when I collapsed took the sequence of tori with cone points, but collapsed them to an arc. Okay, so I have one final geometry, one that hopefully will be maybe a little more familiar to many of you. And this is where I get to say minimal. So this is the case of sol geometry or solvable geometry. The model space is again 3-dimensional, R3. I didn't write this down, but then let's see. Just want to get the sign that corresponds to the take the thing that preserves this metric. Here. So this is the least symmetric of the Thurston geometries. The symmetry group is essentially 3-dimensional. The stabilizer, say, of that point in the middle there is actually just finite order. But it still has a lot of nice geometry and geometry related to familiar geometry. So you can see if I just say take the dz and dx coordinates, that plane going up here, that as you move up and down, what you see is the things of fixed Euclidean length. Let's see, the way I've written it here, if I go z becomes more and more negative, then something that was unit length up here is now length 1,000,000 and so on in this way. So you actually see a picture of hyperbolic 2 dimensions written in sort of the horocyclic version of it. So this just gives me a copy of hyperbolic 2 space that corresponds to, in fact, you get the same thing for all planes parallel to this, where it hits that plane that I've drawn here in black. In the x-axis. So we see a copy, and this is a totally geodesic copy of hyperbolic 2 space sitting there in blue. We get another copy of hyperbolic 2 space sitting there in green. But it's put in there in sort of the opposite way. This one, the Euclidean length of the same size got bigger as I went down here. In the y direction, it actually gets bigger as you go up in the more in that way over there. So we get these two families of totally geodesic subsurfaces. And then there's, again, if you just look at where z is constant, then obviously we have something that's conformally equivalent to just a flat metric. Now that flat plane, so we have a foliation by flat planes as you vary, as you fix z equal to a constant. And one of the isometries that the main, well, so what do the isometries look like? Well, you just have translations in the Euclidean sense, but then you also have, if you go up, then in one direction things stretch, and in the other direction they squeeze down. Okay. Now, in fact, this plane here and all the parallel ones are not totally geodesic, but they are, in fact, minimal planes. Right? They have, you can sort of see that this, if you remember, the curvature, the two principal curvatures here are the sort of blue direction and the green direction. In one case, it's sort of +1 and going one way and -1 in the other way. And in that way, you can see that you actually have a minimal foliation of this geometry. Now, this is a natural geometry for one particular class of three manifolds, torus bundles over a circle. So if we have a phi taking torus to a torus, and it's so-called a Nosov. So, for example, it can be represented by a matrix, say, of this form here. So it has two eigenvalues, real eigenvalues, one bigger than one less than 1. If you think of that as acting on the plane, but then descending, because these are integer coefficients, you take the torus lattice here, we see one foliation by eigendirections here, another foliation eigendirections here, and this descends to foliation down on the torus. And what does this map do? It stretches in one direction and squeezes in the other direction. And, well, in this case, it's a symmetric matrix, so the foliations are automatically perpendicular, but in general, you can find a flat structure so that they become perpendicular. Well, this geometry was sort of obviously built exactly to describe that, right? So you would have your tori here, and as you move up, you do exactly this stretch squeeze map. So all such three manifolds have this solid geometry, and in fact, effectively, these are the only, up to some sort of finite index, these are the only closed three manifolds that have the solid geometry. And for this reason, perhaps it hasn't been studied as much. I mean, this sort of not a finite class, but a fairly understood class. But as I hope to show, I think this is the same picture will actually be quite useful in general, but particular in this audience, mention that this not only has a solid geometry, but it has a minimal foliation by tori, okay, coming from these guys here. Now, if you take, say, the origin here, and you take that orbit doesn't move at all. So when you form the mapping torus here, you get a closed curve corresponding to the orbit of the origin. You can remove that and get a punctured torus bundle. In fact, if you use this one, you get the figure 8 knot complement. And in fact, those manifolds actually have complete hyperbolic structures. So if you remove the orbit of the origin, then in fact, and now you have a manifold, an open manifold with an end that looks like a torus cross R. You, in fact, can get a hyperbolic structure, a complete hyperbolic structure on that. And in Thurston's notes, he actually analyzed that you could go through cone manifolds from the complete structure, increasing the cone angle all the way down to 2 pi, and then collapsing in a certain sense to the Sol structure. Well, in fact, what you actually collapse to is to one of these copies of hyperbolic plane that you see inside of there. And in fact, by conjugation, you can get it to collapse to either one of them. Now, this analysis was worked out for all of these cases by Husner, Porti, and Suarez. They proved the same thing happened, that you could start with a complete hyperbolic structure, increase down to cone angle 2 pi, and degenerate in a certain way that you could see the collapse or see the transition to solid geometry. Now, they didn't describe it in terms of this transition idea. And one thing I want to actually kind of emphasize here is that the natural geometry on this manifold before we took the orbit out is sort of obviously the solid geometry. So that's, you can think of almost given to you. So you can think of, well, what if we started with this solid geometry? We have an orbit that has a cone angle of 2 pi at that. Can we perturb it in such a way that we get hyperbolic structures with cone angle a little less than 2 pi and go back the other way? And in fact, that's essentially what you can read off of the Husner-Portis-Suarez idea here. And from that point of view, you can actually prove, so the fact that this has a hyperbolic structure, a complete hyperbolic structure, either comes from Thurston's what's it called? Sufficiently large. His hyperbolization theorem, and you can do it other ways. But this actually gives another way to prove that you can find a complete hyperbolic structure, because you can actually start with the complete the solid structure and move back to the solid structure. Now, the work of Jeff Danziger actually shows that, in fact, you can do a transition and get these sort of singular ADS structures on these manifolds as well. Okay, but then the final slide here is, what about higher genus? Okay, so we do actually know that if we take what's called a pseudo-Anosov map of a higher genus surface to itself, I mean, Thurston proves that it has a hyperbolic structure. But that's a fairly, well, it's a very hard theorem, and it's also not so clear how the hyperbolic structure is related to this pseudo-Anosov map. Now, it hasn't really been, we've talked about pseudo-Anosov maps in a number of cases, a number of talks here, but one of the main structures or descriptions of it is on the surface, what do you see? You see 2 transverse measured foliations. In fact, they can be defined in such a way that can define a flat metric. Now, they necessarily so that these things are orthogonal. Since it's a higher genus surface, you need some kind of singularities. And in fact, they all have cone angles here. So you see a flat metric with cone angle of k times pi, where k corresponds to the number of prongs in any given color there. So this would have a cone angle of 4 pi sitting in there. And so almost a definition of pseudo-Anosov is that the map takes those 2 transverse orthogonal foliations, which you can also think of as coming from a quadratic differential. It expands in one direction and it squeezes down in another direction. That changes the conformal structure and gives you a new thing in that form. Okay. Well, again, you see staring at you a solid structure. It's just it now has the singularities. So any such, so this shows very sort of clearly that there is a singular solid structure on any such mapping torus for a pseudo-Anosov map, and it comes very naturally from the definition of pseudo-Anosov. And again, this will give you a foliation by minimal surfaces. I don't know if these have any interest whatsoever to the people who, because of all the singular metric and so on. But there are, in fact, you know, for all of these, there is this sort of naturally lying around singular solid structure and in fact, this minimal foliation by these singular surfaces with singular flat metrics in them. Now, you can ask, and the way I sort of got interested in this was, can you do like we did in the torus case, and is there some kind of transition from the singular solid structure? Can you decrease the cone angles a little bit and turn it into a singular hyperbolic structure? Okay. Now, the dream, it's been a dream since I was a grad student, so a long time ago, of reproving Thurston's hyperbolization for these mapping tori by taking this singular solid structure and decreasing the cone angles, not all the way back to 0, but back to 2 pi. Okay, but there's been essentially 0 progress on this since whenever. And so a couple years ago, Kenji Kozai actually did prove you can do this if you have some extra conditions on the foliations both being orientable and some statement about the action on the cohomology. So this actually implies that the cohomology, the first cohomology of the mapping torus actually has Betti number 1. So at any rate, I won't go through this, and this is a little description of the relation between HP and sol geometry. But the point is he did prove at least you could get started with this process. So we don't have very good control yet over how to decrease, whether we can decrease back to the cone angle 2 pi, but at least we have a start. Okay, thank you.
Right, any questions?
In the transition from the quasi-Fuchsian into ADS geometry, is there also a topology change that occurs?
Topology on the underlying manifold? Yeah. No, it's still, but it's still going to be a cone manifold. And the notion of what a cone angle or whatever changes to the ADS version. It's tachyon. I mean, at any rate, it's some sort of, instead of being a rotation, it looks like a one-dimensional hyperbolic sort of thing. So you have to sort of redefine cone structure, but it's still, yeah, it still gives you, again, these will be singular structures, and, you know, but there will be, so this shows that many, many three manifolds, in fact, have, you know, these singular ADS structures and so on. There's very little known. None of the local rigidity theory carries through, and in fact, for smooth ADS manifolds, they're not rigid at all. But at any rate, there's a lot of work going on. When there are singularities, it almost seems like there's more rigidity, but that's being studied now.
Any other questions? No? Okay, well, let's thank Steve again.